Today I'm going to teach you how to make an electric generator, AC generator from an induction motor. This looks like BLDC, but it is mono block pump with a power rating of around 100 watts, 0.5 amps, 220 volts, and rest the power factor. As you can see guys, that the shaft is running really smooth, indicating that there are no magnets inside and it's an induction motor. And guys, because it's a pump, these two pieces were also connected to its head, and internally they contained an impeller for performing the pumping action. And you can imagine now how it looked. Okay, so let's remove this. Now guys, at the back of it you can see 4 terminals. Okay, 2 are for starting the motor, to which the capacitor will be connected, and these 2, the red ones, are for the main winding. So guys, here as you can see that I'm connecting the meter terminals to the main running winding of the induction motor, which are the red ones. And the meter, as you can see, is pointed at AC voltage measurement mode. The starter windings are not connected anywhere, they are just left open. And now I'm going to run the shaft and hope that it generates some voltage. You can see that it is generating very little voltage, somewhere around 0.07 volts, which is very less. So I decided to couple the shaft with this cordless drill and then try. Okay, now let's hope that it generates some good amount of voltage. So at full speed it is generating around 0.2 volts AC, which is very less. And that was because an induction motor contains a squirrel cage rotor without magnets. Okay, so let's open it up and do some modifications and then try. Now guys, yesterday I saw a video on how to convert an induction motor into an electric generator, posted by Great Scott. Yes, I follow him and really like his content, but I have a different point of opinion on the fact if induction motors can be converted to generators. Like he said that they are not useful as a generator and they generate around 2 volts or something like that, which is not useful at all. And if you want to use it as a generator, then you will have to either modify the windings or use stronger magnets. Now guys, this what you see is my custom made rotor field from an old DC armature, and the magnets are from a 775 small DC motor, and that also not the strong ones, only the ferrite magnets, not the neodymium magnets, which I'm using here to induce EMF in the armature windings of the induction motor and see how much voltage it generates. So let's try that. Here as you can see that I've placed a bearing, okay, and the black wires I've taped them over here on the yoke because they were getting in the way of testing. So okay, it's like this, and I'm going to measure the voltage or generate electricity from these 2 wires. I mean, it is going to be present on these 2 also, but I'm not going to like measure it with a meter or utilize it. Okay, now one thing you will notice, okay, this is the winding, and that's the core and the armature. Now when I'm going to place this magnet, the field winding, the field, not the winding, because it contains magnets, and place it through the hole of the bearing, okay, there is a lot of air gap. I'll show you. You see the air gap, so much air gap is present, so the voltage that is going to be induced is also going to be really less. So then also considering that, you will see the generated voltage is going to be much more. So guys, here as you can see that I am connecting a cordless drill so that I can rotate the field and the induction motor can act as a generator and generate electricity. So guys, here as you can see that there is a little movement of the drill, no rotation at all, and still it is generating some voltage. So let's start it. You see that it is easily generating around 6.7 volts. Let's try and go a little more. 7, 11, so 12.17 volts AC was the max I could do with just two poles. So much air gap between the field poles and the armature, and also the lowest quality of magnetic poles, the ferrite poles, and that also very small and too old from a 775 motor. And yes, I have also not utilized the output voltage from the starter winding, these two. So let's do the measurement for these also. Keep watching the display screen of the multimeter. You see around 13 volts is the voltage produced from the starter winding. So 12 volts from the main winding and 13 from the starter winding. Now guys, this is an 84 LED panel. Okay, I haven't tested it. I don't know how beautiful it is going to glow and how much output illumination it is going to give. But still, let's see if it works or not. Okay, you see the flickering is because the output is AC, obviously. So let's turn off the lab lights and then see how much the output illuminance is. So guys, the lights are out except for the camera flash. Okay, you can see how bright it is. Let's turn off the camera flash as well. Now all the 84 LEDs except for these three, I don't know why they're glowing so little, but yeah, rest of them are working just great. Yeah, I think I found one more over here. I don't know much about it, but there's a little pointed towards the top and below. That is the max variation that I am getting over here. And the frequency that you can see is only 21.36 Hertz. That depends on the RPM that I'm giving it here. I will reduce the speed, then you will see the frequency. You see 9 and 10 Hertz, and if I increase it, 21 Hertz. Okay, and so we can reach 50 or 60 Hertz according to our requirement. So yes, the output sine wave is also pretty good, and the output generated voltage is also very good. And guys, if we use a bridge rectifier, we can get a constant output DC also. You see, still there is a little bit flickering present, and that can be eliminated by connecting an output DC capacitor across the two terminals. You see, pretty good, right? Let's turn off my camera lights. Still glowing and slowing down because of the charge left in the capacitor. So guys, I believe that was enough proof for you that an induction motor can be converted into an electric generator, an okay one. I'm not going to say a great one, but yes, it can be converted and utilized as an electric generator. But now comes the part why it didn't work when Great Scott tried it. Now guys, let's assume that this one is one of the induction motor coils in its armature, okay, and this is its rotor, the squirrel cage rotor, and we have managed to place a magnet on this side and one on this side. Okay, so the coil is like this and the magnet is like this, and this one is north, the magnet, this one is north, okay, and this one is south, this side. So like it moves like this, then it induces voltage, and then again when this magnet comes, then it induces reverse voltage, so it produces pure sine wave AC. Okay, that is easy. But what will happen if we place the magnets too close to each other? That happens when we like introduce many magnets, like as Mr. Scott did. What he did was he used like 8 magnets, because of which they were too close to each other. This time when it comes, then you see and you tell me what will happen. Okay, what do you see? You see 2 magnets inside, so the 2 magnets are inducing EMF in the same coil. Let's say this portion of the magnet, the surface is north. Okay, this north side of this magnet is going to induce south on the front side of the magnet. This side is the front side of the magnet. Okay, it is going to induce south over here and north at the back. And at the same time, this is having south on its surface, the other magnet. So this magnet is going to induce north on the front and south at the back. So they both are going to fight each other, and whichever is a little stronger than the other one, that is going to override the other one. And the difference between the strength of magnetism is the only available magnetism that is going to induce voltage in the coil, and hence very small output generated voltage. This what you see is an expensive 100 watts LED light Lustreon. The operating voltage range of this LED light is 110 volts to 220 volts. And in total I have 10 pieces of these. So when I connected this one, you see it burned out. You see this was some kind of capacitor and it blew. So after that I tried operating another LED panel, but at lower voltage, like reducing it to 120 or 130 volts, and it worked perfectly. So guys, when I investigated the problem, I found out that the voltage that we get from our home socket is much more than just 220 volts. It is as high as, you can see, 240 volts AC, because of which my LED light got destroyed. So guys, to eliminate this problem and safely operate my expensive LED lights, I found this solution. Now guys, the first question that I want to ask you guys in this video, and you have to answer it truthfully in the comments. How many of you knew that even 120 volts Zener diodes exist in the market? And this one is the second piece for this circuit. It is MJE13009 power transistor with a voltage rating max of up to 400 volts. So guys, starting with the first part, which is the oxidation removal on the terminals of these two components, okay, the rectifier and the power transistor. Okay, so for that I'm going to use this Dremel tool, mini Dremel. So guys, after that, place the rectifier in such a way that the positive terminal faces you, okay? So now comes the soldering part. So guys, you see how beautifully I've placed it finally. It is shiny. I can almost see my finger reflection, okay? It is perfect. Now guys, after this being done, remove it and then take the power transistor, and I have one more empty arm over here. Place it like this and then fold the terminal, the emitter one and the base one, and the collector terminal will remain as it is. Now place some flux for better soldering. Okay, yeah, that is good enough. So here, as you can see guys, the positive terminal of this power transistor is in direct contact with the positive terminal of the bridge rectifier. This is the Zener diode that I'm going to use for this project, as I have already showed you. It is 120 volts. So this is positive, that is for sure. Collector is positive and this terminal from the rectifier is positive, but the Zener diodes are connected in the reverse direction, and for a diode the silver side represents the negative. So the negative terminal will be connected over here. It is going to be something like this. So let's place some flux on this terminal also. That's done. Okay, so starting with the soldering. Yeah, you see a perfect connection for the three pieces, the rectifier, the transistor and the Zener diode. Now the positive terminal of the Zener diode will be connected to the base of the transistor, okay, like this, and done. So guys, after completing, the circuit will look something like this. Okay, pretty good soldering, and everything is in place exactly how I want it, and the two terminals are separate. Now comes the wire that I'm going to use here. Well, this much length is good enough. Now guys, here as you can see that this one terminal coming out from the power transistor, this one is the emitter. So to this emitter terminal I am going to connect this green wire. Now guys, after that being done, all that is left is connecting the connector cables. Okay, so let's find the AC terminals first. You see this is positive, this one is like a sine wave sign, so this is AC, and its diagonal opposite is also AC. So to the AC terminals I'm going to connect the blue terminals. Both the blue wires will be connected to the AC. So these blue wires are for 220 volts input AC supply, which is actually 240 volts as I showed you, and the remaining terminal you see that is the negative terminal. This is positive, you see, of the rectifier, so its diagonal opposite is the negative, and done. So these two, the green and the green, are going to be the output terminals, and the blue and the blue are going to be the input terminals. So let's check it and see how it performs. So guys, the heatsink has also been connected. Now let's try it. Now guys, this is the 240 volts AC supply I am getting. So let's check it before operating. Now here, as you can see, that it is 242.8, almost 243 volts. For safety purposes, I have turned off the supply, and now I'm going to connect the blue terminals to this pin directly. Okay, the supply is turned off. Okay, so I'm going to turn on the supply. Now let's measure the output at the two terminals. And as you can see that we are getting only 117 or 118 volts, which is safe for our supply. Yeah, 117 or 18. Perfect. Even 116. Okay, so guys, now let's connect this 100 watts LED. You see here it is showing 110 volts, 100 watts. So guys, the terminals have been successfully connected. Now let's turn the supply on. Whoa! Working really nice. Great. Turned off. Let's turn it on again. And we have a very safe, perfectly working circuit. Well guys, I also wanted to try and test this powerful large DC motor, since the output from this circuit is DC, so it can work for that part as well. Okay, so the connections have been made to the circuit, you see, and this is the earth wire, not needed. Now let's connect the terminals of the mains. Although it is turned off right now, I will turn it on after the connections. So guys, the connections have been made. All I have to do is turn the supply on and it should start working. Okay, so keep watching the motor, guys. Go. Well guys, how foolish of me, because I never thought that the torque was going to be so high. But the good thing is that the circuit built was very strong, because of which it didn't get damaged, although the transistor is bent a little bit, but the sheet is damaged, you see. This was a little smaller motor than my normal large motor, so I thought that the torque is not going to be high, and also I'm not going to give it its full input voltage. But as you saw, that was really high and I was wrong. So guys, after installing the gearbox and placing it on the vise, I have replaced the batteries. These batteries are 12 volts each, 7 amps, and this is the BLDC motor speed controller. Link will be provided in the description. You can increase the speed and decrease it with this knob, and this is the anti-clockwise and clockwise moving switch, and the red wire indicates the positive, which is still not connected to this one. So let's connect it, and you can see that it has started running. Torque is very high, almost unstoppable. 200 kg centimeter. Now let's increase the speed further. It is 24 volts. More, full speed. That's the full speed. Yeah, I cannot stop it. 200 kg centimeter, pretty good torque. Now let's move it to anti-clockwise. Starting it. So guys, there as you can see that I've coupled a heavy water pump with that motor, and I'm going to turn it on and see how powerful the motor is, if it can pull it towards itself. And at the same time I will also have to hold the motor itself, because there could be a counteraction. The weight is too heavy, this might get pulled towards that, and this entire setup might go under a short circuit. So let's start. Well guys, this time I've connected a 20 kg load with this rope to the motor. Okay, and I have tied up the motor with another rope so that I don't have to hold it. Okay,